So in the previous lesson, we learned how to calculate the centroid of a cross-section, and from that the second moment of area. What's going to give us a term that describes the rigidity to bending. This is a geometric term. We also learned that if we take a beam and we push on it from the top, it's going to cause bending, and we can look at a shear and moment diagram to calculate the shear forces and the bending moments at any point along the beam's axis. And so now it's important for us to be able to combine these ideas, second moment of area and the applied moment, to determine what the stress is in a bent beam. And so what we'll consider is the pure bending of a prismatic beam. And so that's when we take this beam and apply a positive moment, so this thing is bending in this direction. And what you can see here is that that red line becomes curved. And there's a stress within this structure from this bending deformation. And what we're trying to do now is be able to calculate that stress. So we're going to start with the normal stress. And so what I've drawn here is this beam in the undeformed state. So this orange line running along the x-axis here is the neutral axis. So imagine if you looked at a cross-section of this, and you found the centroid, and then you passed a plane straight through that centroid, that's going to be the neutral axis of this beam. And so initially in its undeformed state, it has horizontal lines that are parallel to the x-axis, and vertical lines parallel to the y-axis. As we apply a moment, counterclockwise, a positive moment m sub z, this thing is going to bend kind of into a U-shaped structure. And now, a few things we'll notice right off the bat. The initially parallel straight lines that are running horizontal on the undeformed beam now have a curvature to them. The vertical lines that were parallel to the y-axis remain straight, except now they've splayed a little bit. They have a little bit of rotation to them. And so, in the case here where they're perpendicular, running through the cross-section here, in this case there's a bit of splay. And this has an important consequence, which you can possibly see right from the outset, which is that in this undeformed case, the length between here and here, some arbitrary point, we can denote it as delta x. And as you go here and look at the deformed case, what you should start to see is that at the top of the beam, this delta x, so maybe we'll call it delta x prime, at the top is now smaller than this initial case, and at the bottom, from this kind of splayed angle here, this delta x prime at the bottom is larger. So what you should be able to see right from the bat is that the top of the beam, what I denoted with this red line here, is actually in compression. 2 points along the beam, here and here, have now moved closer together. And so they've been compressed. And the opposite is true with the other side of the beam. 2 points that are initially some distance apart are now in tension. These points have moved further apart. And so we want to be able to describe that strain that we're observing there, this tensile and compressive strain. And so what we can do is kind of look at that delta x segment of our beam. So here's an element delta x, and our neutral axis will run here in the x-axis. From the centroid we'll go up to the y-axis. And then what we can do is look at an arbitrary point some distance y up the beam's cross-section. So this will be our distance y, and we'll call this a new length delta s. And so what you can see right from the initial drawing here is that in the undeformed state, delta s is just simply equal to delta x. But as we deform this structure, our neutral axis remains the same length, hence the name. It's a neutral axis. If we have compression at the top and tension at the bottom, at some point along this cross-section, there has to be no change in length. And that point occurs at the neutral axis of the beam. And so what we can do is try to determine the strain as you go down the y-axis of the beam. And so what we can do is look at some point, and from that point, we'll make an angle here, which we can call delta theta. And that angle is basically describing how much curvature is being induced from bending the structure. And the way that curvature is measured is we can think of that neutral axis of the beam. We can go back to the same point, and if we draw a line from that point there to the neutral axis, this is described as the radius of curvature of this bent beam. And all that's basically saying is we're taking a flat structure, we're bending it into something that starts to look like a circle. And what's the radius of the circle that we're bending it in? And that radius is given by rho. And so now we can get back and think about that arbitrary point I drew, which was, say, here, a distance y. And we can call this delta s prime. And so what I want us to be able to do now is think about our definition of normal strain. And so our definition of normal strain was that epsilon was equal to this new length minus that old length, delta s, over delta s, as we take the limit of delta s going to 0. And so what does that mean in this drawing here? Well, what we can do is we can redefine delta s, which is kind of this distance here, and we can call delta s as equal to basically the arc length of this curve. So that would be a rho, a radius of curvature, times the angle. So it's rho times delta theta. And we can do the same thing at some point y. So now we have to account for the fact that if we move some distance y from the origin, that this length is going to be shorter. And so what that means is that delta s prime is equal to rho minus y times delta theta. And now using these definitions of delta s and delta s prime, we can rewrite our strain as rho minus y times delta theta minus rho delta theta over rho delta theta. And now we've substituted delta theta for our delta s here, and so what we want to do is take the limit of this equation as delta theta goes to 0. And if we take the limit of this term as delta theta goes to 0, what we get is that our normal strain will be equal to negative y over rho and that makes sense. That's completely in line with what our initial qualitative description, right? If we start here at y equals 0, we said there's going to be no strain at the neutral axis. Well, y equals 0 gives an epsilon, a strain, normal strain of 0. If we go up this some distance y, we'd put in a positive y into that equation, and we would get a negative normal strain, which corresponds to compression. And vice versa, if we start at our origin and go down to some arbitrary point down here, we would put in a negative y, and then our strain becomes positive. The other thing that this tells us is that, kind of even as we can see from this drawing, is that our maximum value of our strain is going to occur the furthest distance away from the neutral axis. And just like we did with torsion, we can define that furthest distance from the neutral axis as c. That's where our maximum strain is going to occur, on the outer edge, both the top and the bottom, if the neutral axis runs down the center. And so we can redefine this being relative to the edge of the beam and say that stress will equal negative y over c times our maximum strain. So this gives us a relationship between strain and where we are along the cross section of our member. If we want to get to stress, we can recall Hooke's law. You know, if we recall that stress is linearly proportional to strain, and we know from this equation that strain is linearly proportional to y, we can replace this with our stress, it's going to equal negative y over c times our maximum stress. And it's at this point that we need to get a better description of what our stress is. We need to know what our stress is relative to the moment that we're applying here. And so what we can do is we can draw our cross-section again. So I'll redraw this up here, such that here's our origin. And so we're looking at the z-axis there, y-axis, and the x-axis, which is the longitudinal axis of the structure. And we're applying a moment about z, mz. And what we'll do to get a sense of the stress here is look at a tiny area element, dA, which exists some distance y from the origin. And now this is feeling a force here, a differential force F, induced from that moment. And so what we can do is sum our moments about the z-axis and set that equal to 0. And if we sum our moments about the z-axis, what we find is that 0 is going to equal, we're going to integrate over the area, and we're going to have whatever distance we are from the origin, y, times that force element. We're basically breaking up that moment into its force and its arm. And now we know that we can write our stress, so this can now become y times our normal stress times our area element. So now this gets us our integral over the area, stress times dA. And here's where we can put our relationship of stress to stress max into here. And if we do that, what we see is that we should have integral over the area of y times negative y over c sigma max times dA. Sorry, this shouldn't be equal to 0. This should be equal to our moment. And so I can write that here as well. So our moment is going to be equal to the integral of y squared over c times sigma max. So some of these things we can pull out of this integral, right? So we can rewrite this as negative sigma max, which doesn't vary as a function of y, c, which doesn't vary as a function of y, times the integral of y squared dA. And this should look familiar, right, from our last lesson. This term here is going to be our second moment of area. And so now we can simply write that our maximum stress from this equation here, sigma max, is just going to simply equal our applied moment times c over I. The minus sign goes away because c is going to end up being, this is going to end up being an absolute value depending on where we go for the top and bottom. But what we can do is, just like we did here, where we went from kind of our stress relative to the radius of curvature to our stress relative to the edge, is we can take this and say that our stress, and this is our normal stress in the x direction, it's going to be a function of y. So as we move along the y-axis of the cross-section, it's going to equal our moment. And remember that we're dealing with a moment about the z-axis here, so let's write this more explicitly as mz times y. This is going to give us our point along the y-axis. This is a function of y, right? Over our second moment of area. And these things always have to match. It's your second moment of area about the z-axis. How rigid is this thing to bending about the z-axis? And so this gives us what's known as the flexural formula, or the normal stress that amounts from bending. So we've just determined what the normal stress in the x direction is as a function of y. That means how much stress is there as this thing stretches or compresses in this x direction. And we know that to be equal to the negative of the moment about the z-axis times where you are along the y-axis over the second moment of area about the z-axis. And as you'd expect, if y equals 0, if there's no strain there, there's no stress there. And this works really well when your second moment of area is in line with the direction of your moment. And oftentimes things aren't that simple. So the other important case to consider is you take the same structure with the same coordinate axes, and now we can apply a moment at some angle from any of the axes of interest. And so now in order to determine what's going on here, we have to break this moment down into its components, right? And so this will occur at some angle theta. And so what we can describe is that we will end up with a moment about the z-axis, which is equal to the moment being applied times the cosine of the angle theta. And so this would be like that. And our moment about the y-axis is going to be equal to the moment applied times the sine of our angle theta. And this kind of mixed multiple moments requires us to split up this and to consider both second moments of area. We obviously need a second moment of area about the z-axis to accommodate this moment about the z, and a second moment of area about the y-axis to accommodate the moment about y. And so what this equation becomes is that the normal stress is now going to be a function of both y and z. That's the normal stress in the x direction. And it's going to be equal to what we saw before, the same equation, so negative mz times y over iz. And now we have to add the resistance for the moment about the y direction. So we'll have positive moment sub y times the z, wherever you are along the z-axis, over I sub y. So in this case here, if you look at an arbitrary point, say here, you have some distance z, some distance y. You'll have to be able to calculate your second moments of area about iz and iy. And this, combining these two moments, which you've split up from your applied moment, you can calculate the stress in the x direction.